From today, in waves and oscillation, we are going to start a new chapter, normal modes of continuous system. Actually, in this chapter, we will see a particular method which is called Fourier method to analyze the normal modes of continuous systems. Okay. Actually, previously we have learnt about the oscillations of system having 2 degrees of freedom. When you say oscillations of system having 2 degrees of freedom, it means you are talking about the problem of coupled oscillations. And you can remember, I have already provided videos on these coupled oscillations previously. Actually, in that chapter, when you first of all talked about the system having 2 degrees of freedom, later on you have seen that in the same chapter we have studied the oscillations of systems having n degrees of freedom, where n is a finite number. Okay? So when you say that we have discussed the problem of coupled oscillations where n oscillators have been coupled, where n is a finite number. Okay. In fact, we have seen that a system with n degrees of freedom has exactly n normal modes. Okay. If the system has n degrees of freedom, then it has n normal modes. Already you have discussed in our previous videos. Okay? Actually, each mode has its own characteristic frequency and its own characteristic shape and configuration. We have also seen this fact in my previous videos on the chapter, in the chapter coupled oscillations. Okay? In fact, in each mode, all the moving parts of the system pass through the equilibrium positions simultaneously. That is, each moving part has the same constant phase which is determined by the initial conditions. Okay? And as here n is a finite number, and you have seen in my lectures on coupled oscillations that the idea which we have developed in the chapter coupled oscillations that are actually applicable to the discrete system. When you talk about the discrete system, what does it mean? It means you are talking about the systems whose mass is concentrated at 2 or a finite number of points. That is called a system of discrete. That is called discrete systems. And we have learned only about these discrete systems. But here, as I have told you, that now we are going to see the problem of finding the normal modes of continuous systems. So, in this first lecture on this normal modes of continuous system, I am just giving you a brief introduction. What we have learnt in the chapter coupled oscillations and what now you are going to learn, and what is the basic difference and how we can utilize the idea developed in the chapter coupled oscillations in this case. Actually, I will introduce these facts in this introductory lecture. And after this introduction, we will start the basic theory of this chapter, which will be very interesting to you. Okay? So, as I have told you that when you talk about the normal modes of coupled oscillations, then you talk about the discrete system, which means systems whose mass is concentrated at 2 or a finite number of points. Okay? Actually, the systems we come across in nature are not so simple, which you have learnt. The practical examples of the system are not so simple as we have discussed earlier. For example, you can take a vibrating string of a violin. If you talk about a vibrating string of a violin, okay, then you can see that the mass of the string is not distributed in discrete manner. This is your string, and you can't say that mass of this string is concentrated at this point, at this point, at this point, and at this point. But this mass is distributed in a continuous manner along the length of the string. Okay? So you can say that the string is not a discrete system, it is a continuous system. Okay? It means the mass of the string is spread uniformly along its length. Okay? Although mass distribution may be non-uniform, but in most of the theoretical case, we will consider a string whose linear mass density will be constant. That is, mass per unit length will be constant. That is called uniform distribution. But if mass per unit length will be not constant, then that will be a non-uniform distribution. In mathematical problem, in numerical problem, we will also see the problems related to a string with non-uniform mass distribution. Okay? But in general, you take a string whose mass is not concentrated at particular points, but it is distributed uniformly along the length of the string, and so it is called a continuous mass distribution. Okay? There is a very good another example you can take. You have definitely seen the loudspeaker. And do you know about the diaphragm of the loudspeaker? In fact, in case of loudspeaker diaphragm, the mass is not distributed in discontinuous or discrete manner, but the mass of a loudspeaker diaphragm is distributed uniformly over its extent. Okay? So these are some of the practical examples where you find that mass distribution is not discrete. So the theory which we have developed in our previous videos, that is not of great practical importance. But gathering the ideas which we have developed in our previous videos in the chapter coupled oscillations, that can be used after some modification in case of the system of continuous mass distribution. Okay? Problem will remain same. Again we will have to find the normal modes of vibration, the characteristic eigenfrequency. Okay? All these things, problem will remain same. But now system is different, and so the method which will be followed to solve such a problem will be something different. Okay? And our aim in this present chapter is to learn this new thing. Okay? Actually, when you talk about the systems of continuous mass distribution, then each particle of the system will vibrate with somewhat different motion that from that any other particle, and it will not be sufficient to specify the motion of a few particles. Actually, the motion of every particle of such a system must be specified. Okay? Actually, in principle, when you talk about the problem of continuous system, that problem can be tackled by considering the motion of n equally spaced coupled masses, as you have learnt in my previous videos, and letting the number n, which is actually represents the number of particles or number of points where mass is concentrated, go to infinity, and the interparticle separation go to 0. Okay? So if you want to handle or you want to tackle this problem on the basis of the idea developed for the coupled masses system, you can consider that there is a chain of particles containing a large number of particles n, which simply tends to infinity. Okay, and the separation between two consecutive or two successive particles, if say it is d, then d tends to 0. So when d will tend to 0 and n will tend to 0, then you can say that this system of particle is a continuous system. Okay, so I have mentioned it here. You can see that in principle the problem of continuous system can be handled or can be tackled by considering the motion of n equally spaced masses letting n tending towards infinity, and the interparticle separation, which I have assumed here d, that tends to 0. So when we will make these two assumptions, actually in that very condition our system will become a continuous mass distribution system. Okay, and we would then when we talk about this such a system, then you will see that there will be an infinite number of equations of motion. Why infinite number of equations of motion? Because you know there will be actually equation of motion for each particle. So if the number of particle is n, then there will be n equations of motion. And if you consider that this n tends to infinity, then you can say that the number of equations will be infinity. So there will be infinite number of equations of motion, because there will be one equation for each particle. Okay, and these equations could in principle be solved to give the motion of every one of the infinite particles. And we would expect the system to have an infinite number of normal modes, and each mode having its own characteristic frequency, as you have learned earlier. So this will be a hopeless task, since the number of equations of motion is infinite. Okay, and for getting the characteristic frequency of vibration, you have to solve all the equations of motion. Can you solve infinite number of equations of motion? So this is a tedious task. This is completely impractical. So I am telling you that this will be a hopeless task and a very awkward way of solving the problem that is essentially simple. The problem is simple, but you are following a method which will make this problem unsolvable. Okay? What is needed actually is now a new point of view, and this new method of attack is called actually continuous approximation. Okay? So for getting rid of this awkward situation of solving the infinite number of equations, we will actually follow an approximate method, okay, to solve such problems. And such an approximate method is called continuous approximation. Actually, you know, in physics at different places, we study different type of approximate methods to handle a complicated problem, to get rid of mathematical rigorness. Okay. So, how this problem will be solved? The technique is known as continuous approximation. Okay. Actually, if system consists of a very large number of particles, which we shall loosely call infinite, okay, infinite number of particles, And if these particles are packed within a limited region of space, let us say this is a cylindrical region, and infinite number of particles are packed in this medium. This is also called bonded medium. Okay. So if these infinite number of particles will be packed within a limited region of space, then the average distance between the neighboring particles will become what? Can you say? Since the region is limited, we consider that there is a cylinder of length L and there will be something, its radius, let us say r. So its volume will be pi r square L, which is a finite volume. And you consider that an infinite number of particles has been inserted inside this cylinder. Then definitely each and every particle will be in contact of one another. Okay? No two particles will be separated by a finite separation. And so in this condition, you may say that the distance between two neighboring particles will approach to zero. If you consider that d is the separation between two neighboring particles, definitely in this condition this d will tend to 0. Okay? So as an approximation, we may imagine the number of particles as becoming infinity and the interparticle separation tending to 0. Okay? And we assume that the system then behaves as if it were continuous. In this condition, such a system will be treated like a continuous system. Okay? In fact, this assumption implies that the motion of near neighbors is very nearly same. Okay? Very nearly same. And we can then divide the system into infinitesimally small elements. How this problem will be then handled? Then you can't consider the motion of individual particle. Actually, in this condition, we consider that our medium is actually composed of small elements, not individual particles. Although an element will consist of a large number of particles too. But we can divide the system into infinitesimally small cubes, you can say, or the elements, and describe the motion of the elements, ignoring the details of the motion of individual particles in the given element. There is no need to consider the motion of the particles in this element. You have to consider the motion of this element. Okay? Actually, this is called the continuous approximation. This technique is called continuous approximation. And when this description is used to replace the description using the displacements of individual particles, we simply say that we are dealing with waves. In this situation, we simply say that we are talking about waves. Okay? So in this way, the idea of waves get generated. The idea of waves comes out in the picture. Okay? In other words, you can also say that waves will be automatically emerge from our analysis of continuous system. Whenever you will talk about the vibration of continuous system, definitely that will be dealt in terms of the idea of waves. I have already provided the basic mathematical aspect of waves earlier in my video. You can see the playlist of waves and oscillation, where you will see what is the differential equation, what is the classical differential equation of a wave, how this differential equation can be solved. All these things I have already uploaded earlier. And before watching the videos on waves, you must watch those. Okay? But in this chapter, we will not talk about the wave motion in detail, okay? Because waves will be separately dealt with in my different videos in the next chapter, okay? Here in this chapter, we shall only use this description to study the normal modes and general motion of few continuous systems. Particularly in accordance with our syllabus, we will discuss the normal modes of the vibration of a string. That is the most important problem which we will learn previously, and after that we will also see some extra problems. Okay. So this is just a brief introduction regarding this chapter, that is normal modes of continuous system, and how this description will be different from the ideas which we have developed in the coupled oscillations chapter. I think you have clearly understand. Okay. So in my next lecture you will see the most important problem of this chapter, and that will be actually the transverse vibration of a string. Okay. Thank you very much.